Okay, so I have explained what is this function doing. Okay, so this is the main function as its name suggests, but I have written it in assembly. I have loaded the address of num1 and then using that address I am actually getting the value into R0, and this value is got into R1 by first initially loading the address of the variable where it is declared and then moving the value there. Now once the values are moved into R0 and R1, which happen to be num1 and num2, these two are the parameters to this function. Okay, so as per the ARM procedure call, our first parameter will be in R0 and then second parameter will be in R1. If more parameters are to be passed, maximum 4 we can pass through registers R2 and then R3, and if there are more than 4 parameters, then the rest of the remaining parameters will go into the stack. Okay, the calling function will push it into the stack and then call the function. Now because we have only 2 parameters, they are passed through registers, so stack is not used for passing the parameter now. And then branch with a link myadd is called. Myadd is written in C, which has been compiled using mental graphics tool, and I will be showing you the assembly of this. Prior to that, suppose you assume that this is executed and it returns back. It will first what it is doing is it is taking the address of where the variable is into R4 and then the value in R0 is copied there. So it is assumed that this function on returning the return value is kept in R0. So that is also according to the procedure call. So the C compiler which is compiling this particular function follows the ARM procedure call, and based on that I have written this assembly code and I am getting the answer back. So I suggest all the students to try out this particular piece of code. Both this has to be written in C and then compile it and then generate an assembly .s file. Okay, and then you can this S file and this can be multiple S files can be assembly files can be loaded into the simulator. So load both, then run this. So what will happen? This will call this function and then return back, and then you will get the answer. So the result will be back in R0. Okay. So if you are watching these all 3 variables, you will be seeing the sum of this. So you can even change this number as you wish, and then try to see whether it is what you are getting here is the addition of these 2 numbers. Okay. Let us now. So hope this is clear to you. So this main function is calling this routine which was written in C, and now we will see the assembly output of this and then how this is followed. We can combine these two. So this is the C function which I showed you in the last slide. This is the generated output. So I have just taken a assembly listing of the compiled output. Okay, OBJ file will have the binary of this. Okay, the binary encoded values of these instructions, but you can always ask for an output file which is an assembly output. Okay, instead of, because we will not be able to understand OBJ, so we can get an assembly output file from the compiler to see whether the instructions what has been generated by the compiler matches with what we understand this function is doing. Okay, so all these instructions are generated by the compiler. Looking at this definitely C function. Now let us understand what is happening here. So first thing, when you get into a function call, the stack how it is managed is what is more important. Okay, so assume first of all, as I mentioned, the stack is always assumed to be full and descending. Okay, so and R13 is used for the stack pointer. Okay, now full descending means it is pointing at something which is already filled with some value. Now inside the function, if anything needs to be pushed into the stack, first the stack has to be decremented. Okay, so this is the high address and this is the lower address. We don't have to worry about what is the exact start address there. Okay, R13. What is it? Already we are sure that this is initialized. Okay, so we don't have to worry about the actual value, but only the relative value. Whatever is the value that R13 has, with respect to that, how the stack is going to be managed by this function. Okay. Now, first thing what it is doing, the compiler has generated all this code. So this is the first instruction. As soon as the BL myAdd was done, okay, let me link you from that assembly file to this. When this was executed, there was some instruction after this. Okay, let us call it as some XY, XXYZ. Okay, some instruction is there residing at this address. Now, after when this particular BX branch is done, with respect to LR link register, it is supposed to go back to the address next to this BL instruction before this function was called. So where is this address stored? It is stored default in R14. Okay. Who does it? The processor pushes this address. It computes this address. After this instruction, whatever is address, it is pushed into the R14. That means it is the R14 is filled with that value, and then this instruction is executed. Now R15 is modified to point to this instruction. So by this time R14 is already loaded with the instruction next to this BX. Okay, where it is supposed to come back on executing a BX instruction. Okay. Now, as soon as we come into the myAdd, the first instruction is str. Str is the store instruction, storing the value of FP. Here, one more thing what you should understand is FP is a frame pointer. Okay, frame pointer is a register which is R11 in ARM state. Okay, normally, and if it is here ARM state, R11 is a frame pointer, R7 is the frame pointer in thumb state, because thumb state doesn't have the visibility of higher registers. So R0 to R7 only is visible as thumb state. So R7 is assumed to be a thumb state frame pointer. So when a compiler is generating assembly instruction and it knows whether it is generating for ARM state or thumb state, because we would have put code 16 or 32 before that particular C file or C function or whatever, or it could be some other pragma is some instruction to the compiler to see it has to generate whether ARM instruction or a thumb instruction. So based on that it will generate, and accordingly it may allocate resolve FP as R7 in thumb state and R11 in ARM state. Okay, no problem. This FP is a R11. Now R11 is stored in the location. Okay, this is what? This is the post index. Pre-index, because it is subtracting -4 before indexing into this. That means that whatever the value of FP is actually SP is a stack pointer which is always stack pointer which always R13. Okay, so R13 is pointing at some address. It first decrements by 4. That means what? It is pointing at the next empty location, decrementing. So stack is going downwards always, full descending. It is full, so it decremented. Anything to be pushed before that it has to be decremented. Now after decrementing, it is supposed to fill some value. Which value it is filling? It is filling whatever is the SP, it is pushed into this. So SP is what? It is in ARM state, so R11 is pushed into this. Okay. Now what happens? After that the exclamation mark is there. That means the R13 is also now updated. After accessing and then storing this value into that location address, so SP is added subtracted by 4. So SP whatever was R13, that value was subtracted by 4, and then in that location R11 was put, because SP is R11, and then because exclamation was there, the SP is updated now. So SP is now pointing at the new address which is pointing at R11, wherever R11 is stored. Now why is the R11 stored? It is going to be modified. Okay, this right now only hash 0 is there. That means it is not adding anything more to the SP value. Otherwise, it will generate a fixed location. Okay, it will not generate it in the stack. It will be reserving some space. So whatever is the SP value, it will add something to that, so that frame pointer moves further. So inside the function, frame pointer only is considered to be a for accessing a stack. So in this case, in our particular case, there is no requirement of adding more space in the stack. So it is only adding 0. Okay. Otherwise, based on the code that we have written, it may choose something, a different constant based on the local variables or other requirement of stack. It may do it. Now what happens? Now this is SP is added with 0 and then it is loaded into SP. Now in our case, it is same as R13 now. SP is also pointing at the same location. Correct? Because SP is not modified after this addition, so SP is also having the same value. Now FP is pointing. Now you have to remember, SP is pointing at the same location where R13 was pointing. Okay, let me erase it and draw properly. Okay, so FP is also pointing at the same location where R11 is stored, and then this is done. Okay, and then subtract SP from SP 20 value. That means this R13, whatever is there, is subtracted by 20. 20 is what? Decimal value. So let me, so 5 into 4. If each is 4 bytes, the stack is 4 byte wide. So 5 into 4 only is 20. So because this is 4 byte, 5 times the value. Okay, it is going down in the stack. So 1, 2, 3, 4, 5. So stack now is pointing at this location. Okay, R13. Stack pointer, sorry. Stack pointer is pointing at this location, and this is also can be used to fill anything. Why is this done? This is done for this function, particular myAdd function. How much space it wants in the stack, it first grabs that space. What is the requirement? Because if any interrupt happens, the interrupt also may run on the same context, then it may have to use this stack pointer. Or even this function is calling another function, then also there will be a stack usage by the called function. So the depth is undefined. So before anything is done with the stack, it should first, the function which is now getting executed, it takes care of, for local variable it needs some space, and even to keep the return value it needs some stack. So it first gets the stack reserved for itself. Now how is it using them? So to use it, it is accessing it with respect to SP. So once R13 is moved, hereafter any instruction, okay, using the R13 will be pushing the value here or further down. So this is not going to be touched by anybody because R13 has been already advanced downwards. Because stack is going downward, it is advanced downward, so no issues. So these, what are we doing with this? Now let us see what the compiler is trying to do. It is doing -16. It is storing the value in R0 to this. So from SP, wherever SP is pointing, -16 is done. That means it will point to this location. Okay, here it is storing R0 value. Let me change the color. Okay, it is storing R0. What is there in R0? As I told you, R0 has argument 1, arg1. Okay, and R1 will have argument 2. Now this function knows it is expecting 2 arguments because it is been compiled with the 2 functions parameters. So it knows that R0 is having a parameter, so it stores that R0 here. Then you may wonder why is it? No, you can do with R0 itself. You can continue to operate on R0. Why it has to make use of the stack? Because there may be so many instructions which may be needing that value, and then the R0 need can may be used for some other purpose. That is one reason. Another reason is, suppose if this function is calling another function, then that called function will assume that this R0 to R4 is for it to process some parameter R0 to R3, correct? So if this function is calling another function, it needs to be free. So it is better to store it in the stack so that this value is preserved even when the internally, if this function is calling another function also, no issue, because you are already having those values in the stack. So you are not dependent on the value in R0. So R0 is pushed here by this instruction. R1 is pushed into -20. -20 is here. Okay, R1. So R1 and R2 both values have come here. Okay, and then it is load LDR. Now again this value is copied. So 16 is copied to R2 and from this. So actually it is writing into this and then copying from here. So you may see that it's not optimized code, but it is unless you mention some optimization, the compiler is not free to do any optimization. So it does according to whatever we want, because that's why I will be able to explain you what is happening. Okay, so I have not put any optimization, so it is not doing any optimization. So the compiler has is putting the value back into R2. That means we are getting in R2 now we are having the value which was passed in R0, correct? Which was passed in R0 is moved into R2. Similarly, R3 is in this instruction. This instruction is taking the value which was in R1. So it has copied this R0 into stack and then taking it from the stack. So you will effectively get the two parameters here, R2 and R3, and then it is adding R2 plus R3 into R3. So you may wonder how can it use R3, because it is overwriting the value of R2 and R3. It is free to use R2 and R3 because we know as per the AAPS R0 to R3 are some parameters are which is passed into the function, and the function called the function is free to use it. So the caller will not expect these registers to be undisturbed. Okay, it is actually to be used by the callee, the called function. So it is free to use R2 and R3 also, no problem. So that is why it is trying to add this value and putting it into R3 itself. It is not using R4, please remember that. So it is putting into the R3 itself. This is done. So addition of this job, the R1 and R2 is added now, but it has not gone to result. Okay, it is lying in R3, some temporary register. Now R3 is stored into again stack FP -8, which is -8. Okay, this is -4. This is -8. So result is coming here. Okay, the result variable which is declared as a local variable is actually residing here. So it is copying the value R3 into that. After doing immediately it is again taking it back LDR from there to R3. Okay, you may not see some optimization, but it's fine. So now it is getting the value in R3 back. Again the result is now in R3. This is done. This is done. Now R3 is moved into R0. Why? Because it is a return. So this instruction is specific to this return value. So when we are returning a parameter back to the called function, it is supposed to be in R0 to R1. Okay, single value means it is R0, double value is means 64-bit value means R0 and R1. So R0 is what is going to carry the return value. If you remember, that we recall previous function, we were taking the R0 from there, value from R0 and then copying into answer. So R0 is now having the result. Now remember, it actually initially came in with a parameter, now going back with the result. Okay, so R0 is playing a dual role. It brings a parameter R1, it was bringing in, and then now return result, it is taking it back. Okay, while going out from the function. So R0 is now loaded with the result value because R3 is holding that result. I hope this is clear to you. Now what happens is it is, let me erase around this so that now you understood so far up to this instruction. Now what is happening here? It is doing the same thing that was done here. So in case if it was some 4 or 8 or 12, the same will be done here. But here, because it is this compiler is generating the code for any generic purpose, so this 0 will be the same constant is used here. So it actually the SP is getting back, okay, the same value, okay, because SP was decremented here. It was decremented here, but prior to that, SP was loaded with the value with which it started off. Okay, after this -4. So now SP is added to 0 and then getting that SP. SP is now coming back. Okay, it was here -20 was done. Now SP is coming back to this location. I am writing it here so that you understand it. SP is coming back to this location. Original R13 here. Just after coming in, it saved the SP value and then it has come here. Okay, so it was decremented by 20. So SP was changed to prepare, keep in SP prepared for any other function calls to be used. Now if any function call comes, SP can be, R13 can be updated. Now since we are going to go back, the SP is returned to the same location where it was pointing at. Originally SP was loaded here. So the SP comes back to this location, and then now what is happening is whatever SP -4 was done, where the SP was loaded into the stack, now that SP is taken. Okay, so whatever pointing at SP is pointing at is stored into SP. Now this value which was R11, original value which was there in R11, goes back from the stack. So R11 gets its old value, and then because 4 is there, it will be here plus 4 is there, so it will be added. So SP will get added. So it will come, it will become like this value. Before calling, what was this value? Before coming in, what was the value? It goes back to that value after this instruction. You should remember that. After this instruction, SP goes back to the value which it was having prior to entering here. Okay. So as soon as it came, it decremented by 4 and then SP was loaded. Now the SP is copied back, SP is restored. So now what happens? Let me erase everything. Okay, or maybe let me not erase everything. Let me again tell you what is happening here. Okay, so R11 is restored. Now R13 is also restored by this instruction. Okay, because SP gets back its old value and SP is also updated. So this is SP because it gets back from the stack, and stack pointer is again decremented by 4 here. So it incremented by 4 here, which was decremented by 4. So it gets back its old value. So SP and SP are getting back their value. R0 is loaded with the result. So that is what is expected, and you don't have to worry about result. Okay. Now R1 to R3 we don't have to bother because it is supposed to be disturbed by corrupted by the calling routine, no issues, but it does not disturb any other value. If you remember, if you can see that it does not change any other value R4 to anything. It does not, this function has not touched any of them. So it is safe. Now this is executed. Now what happens is R14 is also was not disturbed. Okay, in this it was not saved anywhere. So R14 will be having still the instruction where it is supposed to go back, the address of the instruction where it is supposed to go back. So this will take it back to that location because R14 is not disturbed, it is not modified, so overwritten by any of the instructions here. So R14 is safe. So it will take back the program to the called routine. Means after this call routine where the next instruction is got executed. So this is the flow. So now you may wonder whether the stack, whatever it has pushed, has it gone? Once R13 is updated, the stack is released. Okay, it is as good as releasing the stack because when next any instruction wants to use the stack pointer, it will use from this address only. So no, it will overwrite on this location. So this function uses stack up to this point and then it is released it. You may wonder there were some gaps, that is specific to some implementation of the compiler. So in this particular case it was not used, it is not actually filled with any value, but based on the parameters or based on the functionality which is implemented in this function, it could change. Okay, the compiler behavior might be different. Okay, so effectively if you can see this whole flow, you will be able to appreciate it. Okay, I hope this is clear to you. My intent was to explain you how the parameter passing happens and how the return value is coming from the function. If you understand these two, you will be in a position, because the exact implementation will be different from different compiler, but it will stick to this AAPS convention. Okay, it will always assume the parameters to be in this register, and then it has to return in R0 and R1. These things will be consistent across, but internally how it is using, where it is putting these parameters, and how it is keeping the variable, allocating the place in the stack, there all little bit of freedom is there for the compiler to innovate. Okay, but the correctness is assured by all the compilers. Okay, so I have used this code bench, this version I have used to generate this particular code. So I suggest I will give these references so that you will also be able to generate this code and then verify it for yourself, and then you can write some different functions and look at the output generated so that you can map a C file with the assembly generated. If you can follow what is being done by the compiler in terms of assembly instructions, you have learned the language as well as the architecture very well, and you will be able to debug later on in case if you encounter any problem in the debugging embedded systems that you have built. Okay, so that's it. We have come to an end of this session, and thank you very much for your attention. I hope this was very useful to you. So with this, we are starting the discussion on tools and environment, development environment, and I will talk to you in the next session about some other different topic. And actually, I would like to cover something on linker. Okay, and then with that, we will be ending the discussion on the tools. Okay, thank you very much for your attention. Have a nice day. Bye bye.